Let us start our work. The first speaker is Professor Mikhail Mikhailovich Turov. Please, Mikhail Mikhailovich.
Thank you. Okay.
Please start.
My name is Mikhail Turov, and the topic of my presentation is resolving families of operators and fractional multi-term quasi-linear equations. The first is formulation of problem. They consider the quasi-linear multi-term equations, fractional equations. In these equations, all fractional derivative, the alpha and g beta, it's fractional derivative of Riemann-Liouville, and g beta it's Riemann-Liouville fractional integral. The definition I will be giving on the next slide. About this equation. Here alpha in the left, it's fractional, is the higher order. In the first sum, they have derivative, this the same fractional part as the highest derivative. The second sum is derivative arbitrary and maybe negative or arbitrary. The third sum is the fractional integrals. The nonlinear operator f depend of arbitrary derivatives and alpha L and gamma 1, gamma 2, etc. All gamma I may be negative. And in this equation 1, we have operators AG, BL, and CS. These operators closed linear operators in some Banach space Z.
Sorry, what is the domain for T in the equation 1? T belongs to...
T belongs to 0, 0 to some
empty capital, yes.
Yes. Okay.
Of
derivative. Okay. The fractional derivative of Riemann-Liouville is given by following equality, this equality, and the dm is the derivative of an integer order. That is, in the function f, firstly apply the fractional integrals and then the integer differentiation. The Riemann-Liouville fractional integral is defined by the following formula, this formula. It's definition of Riemann-Liouville integral and derivative. I want to tell a few words about setting the initial conditions for equation 1. Initial conditions must be given for all different fractional paths. We have three sums. Sums 1, 2, they have arbitrary fractional path, and they must have all initial conditions. But in the paper one, they proved that there is a defect of Cauchy type problem. A defect is a deviation of the number of initial conditions from their maximum number. it was proved that all initial conditions are equal to 0 by necessity, besides to the initial conditions for the highest derivative. On the slides, we defined a defect by mu star. Mu star defect is introduced number alpha, alpha 1, gamma 1 plus 1, etc. I note that in this case of linear equation, where was it least on one conditions. Conditions 2 was at least one initial conditions in case of linear equation. In the case of quasi-linear equation, it may turn out that all initial conditions are equal to 0. About defect, I want to demonstrate how defect works or simple examples. Example 1, linear equation. We have highest order 5.5, and we have two fractional derivatives 1/3 and 1/4. In Article 1, it was proved that if where is least one above this one, then the solution goes to infinity. Example, we have one initial conditions d minus 2/3, and for this line we have line above, and for these initial conditions we have line above this line and this line. For the higher order, we have three initial conditions. All line haven't above another line, because we have in this case defect equals 0, defect equals 0, and these conditions minus 2/3 must be 0, and conditions minus 1/3 must be 0 too. For the highest order, they have all initial conditions arbitrary. It's the case the defect equals 0. Now, example 2. In this case, we have fractional derivative 1.9. And this case, we have defect equals 2. What does it mean? It means that only these initial conditions are arbitrary because we haven't line above this case, yes. And for this initial conditional, this and this, we have line above. That is, for example, okay. And in this case, how defect equals to, we have only one initial conditions, only one. Another equals 0, must be equals 0. It's illustration of defect for the linear case. In our case for quasi-linear equation, we have fractional derivative in the nonlinear path, and we defined mu star not only alpha, alpha 1 and alpha n, but and this gamma 1 plus 1, gamma 2 plus 1, etc. Okay. Let's return to the problem, quasi problem. Let's us introduce the notation necessary for the presentation. In these slides, we have operator A, operator B, and operator C. It's closed linear operators in Banach space Z. This domain D, respectively. Define Banach space L from Z. L from Z is space of linear bounded operators. Space D, its intersection of all domain operators, and norm of space D. This operator R lambda was obtained by solving a linear problem, but further some conditions will be imposed on it. Okay. Definition of solution. We have quasi-linear equation 1 and incomplete Cauchy type problem 2, initial conditions 2. This is definition of classical solution. Briefly, everything in equation is defined and continuous. Function z satisfied conditions 2 and equation 1. To formulate the result, they introduce two definitions. The first definition of class A alpha. I don't talk N R A alpha. That typle of operators A, B, C, which are linear and closed in the Banach space, belongs class A alpha if the first D is dense Z. This operator linear and bounded, and the third this operator have a upper estimate in the linear norm for some constant k. Its definition about typal operators belongs some alpha. Two definition. Its definition per resolving families of operator. The definition of resolving families of operator is a generalization of the notion of a C0 semigroup. We have strongly continuous family SP if the first conditions, we do not go beyond the domain of definitions operators, and family SP commutating with all operators, operators A, operators B commutating, and operators C. And for every ZP, SP is a solution of linear problem 1, 2. I write 1, but I write that nonlinear operator equals 0. It's definition of per-resolving families of operator. And now the first result and the theorem, its criterion for the existence of resolving families of operator. This per-resolving families of operator exist. Per-resolving families SP exist if and only if the typal of operators A, B, and C belongs class A alpha. Sorry. Okay. Belongs class A alpha. Moreover, we have the formula to calculate this operator as this formula and operator R lambda. And I want to tell that if initial conditions that are from the space D, then there is unique solution to the linear problem. The second result is the theorem on unique solvability. Its definition of locally Lipschitz, and theorem about unique solvability, local. It's local theorem. Only some segment T0, T1. If the mapping F, it's not linear operation, be local Lipschitz, and then exists T1, that problem 1, 2 has unique solution. Problem 1, 2, it's a quasi-linear equation and initial conditions. Right now, to illustrate abstract results on one class of initial boundary value problems. Take some polynomials, P1, P2, P3, P4, all coefficients A, B, C, D, its complex number, and the least one of the coefficients not equal 0. Let omega be a boundary region, this is smooth boundary, and the operator pencil A, B, B1, B2, and B rho is regularly elliptic. And these formulas for the operators A and B. Now, the defined operators and spaces. Let operator A, A1, and this domain, and for all operators AG, BL, and CS, defined domain DG, DBL, and DCS, and take the space X. I want not take the alpha from 0 to 2 because it's alpha the greatest than or equal to, then all operators will be bounded. Okay, and let H in this equation it's nonlinear operator alpha from 1 to 2, and all alpha, beta, gamma satisfy these inequalities. Determined by the set of the numbers defect M0 star, it's 0 or 1 or 2. And consider the initial value problem 3, 4, 5. Here 3 it's initial conditions, k from mu star 0 m minus 1. 4 it's boundary value or boundary conditions, and 5 it's quasi-linear equation. We have highest order d alpha, and the first sum how equation 1, second sum, and third sum it's fractional integrals, and H it's nonlinear operator. I want note that 3 contained one initial conditions, or they are completely absent if alpha from alpha from 0, 1. We have one or absent conditions. In the case if alpha from 1 to 2, we have two conditions, maybe one conditions, maybe 0 conditions. If 0 condition, this empty set of initial conditions. In particular, for gamma from alpha minus 1, alpha. In this case, we have mu star equal to, and in this case, there is not initial conditions free in the problem. And theorem about unique solvability problems free for 5. Let alpha, beta, gamma satisfy these inequalities, and these inequalities, it's on the dimension of spaces, and nonlinear operator H from this class. Then for some T1 exists unique solution for problem 3, 4, 5. It's all what I want to talk. Thanks for your attention.
Thank you for your very interesting report. Dear colleagues, please questions for Mikhail. Have your questions? Maybe I give the following questions. Do you observe some example of non-uniqueness or non-existence of your problem when the conditions of your theorems are disturbed?
You say about this theorem?
In this and previous theorem too.
Can you repeat, please, your questions?
Some example of the destruction of uniqueness, for example.
Uniqueness.
Excuse me, can I talk as co-author?
Please.
Do you hear me?
Yes, we hear you.
Okay.
Vladimir Evgenievich, please.
Okay. Good afternoon.
Good afternoon.
The simplest example of such kind is problem when initial value data, for example, for the first derivative, first by the order, will be non-zero. It will be not this problem. It will be problem when the smallest order derivative will be equal to non-zero, and then this problem will not have a solution, because this this non-zero data will not allow to exist the solution of this problem for the youngest order derivative, if it will be non-zero.
Okay, thank you for this explanation.
Since it will imply some form of the solution near zero, near the point t0, some property of the power, как поведение, что-то вылетело из головы. Behavior of the power function behavior, and it will not allow to exist a solution. If this, for example, if we will consider cache type problem, but complete cache type problem, not incomplete when the youngest order derivative is 0, then the solution will not exist.
Okay, thank you. Other questions, please? May I give second questions? Mikhail, let us consider the last theorem.
Last theorem. Mm-hmm.
Oh, yes. We have very strong assumption about the nonlinearity function h. It is infinitely differentiable. Is that necessary for your consideration? And if h will have very high but finite differentiability property, does the statement?
In this case,
Yes.
for the proof of this theorem, they used Kozyre's theorem. It's theorem about link Laplace transform and analytical function. We have sectorial operators AP, and Kozyre's theorem about that some nonlinear function h must be class C infinitely, and we used this theorem and because h from this class.
Okay, thank you for this.
Add some remark.
Please.
We need this condition for the acting of the nonlinear operator from our Sobolev spaces into another Sobolev spaces. This condition is sufficient but not necessary.
Okay. Your method based on this property. Okay, thank you. So, have you other questions? If no, let us thank the speaker and his co-author. Thank you very much. And now let us prepare our next